No? Okay. Let's advance into how to solve large linear systems. So here, I'm just going to write the linear system as AU equal to B. Okay, this A may not be the same A as we were writing before. It is actually the same A if you are solving the elliptic equation, solving Poisson's equation. But this A would be, for example, I over delta T minus A if you are actually solving the heat equation. Or it may be a 4x4 block matrix if you are solving using implicit method to solve the hyperbolic equation. But anyway, I'm going to write the matrix you need to solve as a big A. All right. Okay. So, and you also have a right-hand side that is given to you. So you know the matrix A, you know the right-hand side B, and you want to know the solution U. So if you use backslash in MATLAB, it is a pretty magic command because I think there are something like more than 10 possible methods MATLAB can use to solve the matrix equation if you use backslash. So basically, it does a lot of detective work on what matrix you are giving it and what is the structure of the matrix. Is it sparse? Is it symmetric? And things like that. But a common thing between these like 10-ish methods is that they are direct methods. Basically, direct methods perform some kind of factorization on the matrix. An example is the LU factorization. It decomposes the matrix into the product of a lower diagonal matrix and upper diagonal matrix. And that factorization, it basically often does not respect the sparsity of the matrix. So if we have a very sparse matrix like the A we derived at the end of last lecture, like the pentadiagonal matrix, it is sparse in the sense that the non-zero entries in the matrix is much, much fewer than the zero entries in the matrix. Okay, it is very sparse. And during the LU factorization, or most of the factorizations MATLAB performs, the resulting decomposed matrix L and U, for example, is going to be filled up. So L and U is going to be much denser than the original matrix A, even though A is very sparse. The result is that it wastes a lot of operations in comparison to the iterative methods we're going to study, which would only operate on the non-zero entries of the matrix. It basically, the computation cost does not depend on how big the matrix is in many aspects. It only depends on how many non-zeros the matrix have, which is great in our case. Because in finite difference, finite volume, finite element discretizations of PDEs, we usually have a lot more zero entries in the matrix than non-zero entries. All right. Okay, so what is the idea behind iterative methods? I'm going to illustrate the idea using the Jacobi iteration method. Jacobi iteration method, the idea comes from this. An extreme case of a sparse matrix is a diagonal matrix, right? A diagonal matrix is basically only non-zero along the diagonal of the matrix, otherwise it's zero. So if we need to solve a diagonal matrix times U equal to B, what would you do? Can somebody tell me how you would solve this matrix if D is diagonal? Yes? Right, good point. So U is equal to the inverse of the diagonal matrix times B, and the inverse of the diagonal is still a diagonal matrix. And the diagonal entries is just the reciprocal of the diagonal entries of D. So basically UK maybe K is the kth element of the matrix U, is equal to BK divided by DKK, right? Where DKK is the kth element of D, is the diagonal entry. So that's easy. This is a case where the computation cost only depends on how many non-zero entries are in the matrix. It doesn't depend on the size of the total number of entries in the matrix, which is n squared. It only depends on n, which is the non-zero entries in the matrix. So how do we expand or generalize this particular method for this particular matrix into a method that we can use to solve more matrix equations? Well, the idea is I'm going to decompose the matrix A into diagonal and off-diagonal parts. A is going to equal to, let me write it in a more general way, L plus D plus U, where L is a matrix that is equal to the matrix A for all the lower diagonal parts. So if you let's say call the MATLAB SPY function, which we used the last lecture, L would look like something like this. D would look like something like this. It's only non-zero in the diagonal. And U would look like something like this. It's only non-zero above the diagonal. All right. Okay, so what is this decomposition good for? So let's realize if I have a solution U that satisfies this equation, then basically I have L times U plus D times U plus U times U is equal to B. Right? The upper diagonal is big U and the solution is small u. Well, maybe I should make it the notation a little bit clearer by declaring this solution as x. Well, that's fine. Let's keep it u. Okay. And we know that the L and U parts are not invertible because they are not full rank, right? I mean, the number of non-zero rows in the lower diagonal is less than the total number of rows, and the total number of non-zero rows in the upper diagonal is also less than the total number of rows. So they are not invertible. Only D is invertible. So we can write it as D times U is equal to B minus LU plus minus UU. I mean, if U satisfies the matrix equation. Now here is a jump of faith into the Jacobi iteration method. The Jacobi iteration method starts with the initial guess with an arbitrary U0. I'm going to use the parentheses superscript as 0 as the initial guess. And then say for K, let me don't use K here, for I goes from 1 to etc. U of superscript I is equal to D inverse. So basically I'm going to follow the formula on the left hand side here. B minus L times U I minus 1 minus U times U I minus 1. So why am I doing this? I'm doing this because this is easy to do. Because D inverse is trivial to compute. Remember, like when we compute in D inverse times something, it is just equal to that something divided by the diagonal entries of D. Okay. Second, if this thing converges, and what do I mean by converge? If this thing, if the sequence of U superscript I approaches some stationary value as I iterate further and further, if the changes in the sequential consecutive UIs becomes less and less and less, and eventually they become almost the same, then I'm getting back to this equation, right? So if U of superscript I minus 1 and U superscript I are practically the same, and that is equal to U, then basically I have this equation, which is the same as AU equal to B. That means I have solved the equation. That's why I'm doing Jacobi iteration method. Of course, this is under the assumption that the sequential UIs become less and less different. This is not always true. In some cases, it never converges. But for the matrices that this iteration converges, this is a method of solving the equation. Right? We're going to analyze for what matrices this is going to converge. But if it converges, this solves the equation. Any questions on this? Yes? Yes, I start with the arbitrary U0, yes. It is truly just arbitrary. It is arbitrary to the point that in many cases we'll start with U0 just equal to 0 everywhere. Yes, good point. There is a case where U0 is not arbitrary though. When you are solving, let's say in project 2, you are solving the unsteady equation. You know that the solution, which corresponds to the solution at the next time step, shouldn't be too different from the solution at the previous time step. So you can use the solution at the previous time step as the initial guess. That wouldn't affect the rate of convergence, but it'll affect the number of iterations for you to converge because you start with a solution that is close. And we're going to look at why that is the case through the error analysis. Any questions? That's a good question. Yes? So you're asking, we want to do this without the matrix? The answer is yes and no. We want to do this without the matrix being, if you can do it without the matrix being explicitly stored in the computer's memory, that would be better. But we need to do this with the matrix in our head. All right. Yes? Why don't I combine L and U? Why don't we keep it separate? Actually, in this Jacobi iteration method, it's completely fine to combine them. I kept them separate because when we go to the next iteration method, Gauss-Seidel, it makes sense to split L and U. Yes, good point. Looks like you have good understanding of this already. Any other questions? Okay, so I said we want to do this without having the matrices stored in computer. So how is that possible?